In this video, we're going to be talking about training and testing models. In the previous video, we talked about actually building the decision tree using the algorithm to kind of come up with these partitions to split up our data. But there were a lot of different places where we had to maybe make some subjective choices, just some tuning parameters that we had to choose. And so what we want to do is make sure that what we do makes sense overall. And to do that, what we do is, we use these things called training and testing data sets. So let's go into just talking a little bit more about this, supervised learning framework, just to kind of motivate why we're doing this a little more. Right, so if you recall, this is kind of similar to what we saw before. We have that outcome, that label y, and then we have the features x, just the variables that you're going to be using to try to predict y. And what we're doing with machine learning and our decision trees is finding that function f that minimizes future error in recovering y. And the key part here is future error. Basically, we want to make sure that we minimize the error in the future, not in the present or past. And so to do this, we want to make sure that our model generalizes to kind of the overall case, so that when we look at the future, we are able to still have a good model to predict. All right? And so when we have this machine learning model, for example, our decision trees, how do we know it can generalize? Basically, we fit on the data that we have, and so of course it'll fit that data perfectly. We built it based on that data, so we know it works for that data. But that's not all we want. We want to be able to kind of predict the future data points as well. And so for example, consider this case. Basically, if you think about this, this is just the same decision tree that we built before. We might actually look at those red dots at the bottom, the ones that are kind of around the 100 horsepower range, those two red dots that we see. And we think, well, it seems a little bit out of place. That one red dot that's really close to the dashed line and to all of the other, the unsuccessful dots. That one actually looks like it might be kind of like an outlier, or just, it's not near any other red dots. And so, it might seem like, well, that might just be kind of a case where, it was, successful, even though maybe, it maybe shouldn't have been successful, or, maybe that there are a lot of cases, where a similar miles per gallon in horsepower resulted in an unsuccessful campaign, but it just happened to be successful that one time. But in general, if it has similar horsepower miles per gallon, as we can see, by the points that are closest to it, we might want to actually predict that it's unsuccessful because, generally speaking, it's going to be unsuccessful. Right? So when we made these last two partitions, those two vertical dashed lines, we were basically only getting just that one point. Right? We were kind of adding additional, parameters. We were adding kind of additional branches to this tree. And that really, it doesn't really give us very much predictive power in the future. If we, see in the future that a car has horsepower of 100 and miles per gallon of like 20.5, just looking at this intuitively, it looks like we should be predicting that it will be unsuccessful rather than successful, even though it technically kind of falls in that little sliver, right? And basically the idea is that a difference of that narrow band of 20 to 21 miles per gallon, that's not really anything special about it. The only reason we made that split was just because of one data point, one successful campaign, whereas the most of the other data points kind of support the conclusion that really just below a certain horsepower, it seems like they're generally unsuccessful campaigns. And so it looks like what's happening here is that we're really kind of stretching this model a little bit far to kind of fit your one data point. And generally what's going to happen is that because of that, because you kind of stretched it out to fit that one data point, it's not going to generalize well. It's you're not going to find that when you get new data in, it's not going to predict well for the values in that little narrow band because we based our conclusions of this on one data point. And so you know main issue here is that our model isn't generalizable to the overall population, right? Because we fit it to be too specific to kind of our individual data points. And this phenomenon is called overfitting. And you'll hear this a lot in the kind of machine learning world in terms of prediction. Basically, you don't want to overfit. You basically don't want to create a model that's perfectly fitting for your data set. Essentially, what you can do is you can just say, for each of these specific cars, it was unsuccessful because of all of these very specific features. And that will work great on your own data set, but that's not going to work well if you try to add other cars to it. And so because of that, what we do is we want to validate our results. We want to validate our model to make sure that when we add new data points, when we add new cars, that the predictions are something that we can rely on. And so what we do is essentially split up our data. And what we do is just kind of artificially create that future data set that I was talking about earlier. When we're trying to minimize future error, we're essentially kind of artificially creating a future data set. And so what we do is we create this test set that is our future set, and then we have a training set that's the subset that we build the model on. Right? So basically, for example, we might split it just half and half, just 50% training, 50% test. We build on the training set, and then we test on the test set. And so we're losing a little bit in terms of our sample size, but in terms of machine learning, a lot of times we want to have large data sets, and so that's not really a problem. But what we're gaining is the ability to test our model on quote-unquote future data. Right? And so there's a lot of ways to do this selecting train and test splits. One that I just mentioned is just kind of randomly assigning a portion, for example, half, as the training set and the rest as the test set. And so you could just do other splits like 60-40, 70-30. This is kind of like a simple holdout sample. You just hold out part of the data set. That's the test set that you're holding out. And then you train on the rest, and then you build your model, and then you predict on the test set so that you know how well it's doing on this future data set. But what if that test set that we just chose happens to be unusual in some way due to random chance? Right? So it's possible we just randomly pick data points, but it just so happens to be some weird, there's some weird idiosyncrasies in there, so it just so happens that it's not good to test it on that. And to kind of account for that, there's this method called cross-validation. So this is k-fold cross-validation. Basically, to do that, what we do is we split the data into k equal partitions. So for example, if you had 1,000 data points, to do 10-fold cross-validation, you would just split it up into 100 data points each, 10 different partitions. You designate one partition as a test set and the rest as a training set. Fit the model in the training, evaluate on the test set, and choose another, and just basically repeat until every single partition has been set as a test set once. Right? So basically, after each of these iterations, what you're doing is you're building your model on part of the data, and then you're testing it. Basically, you're just kind of seeing how well those predictions do, and kind of evaluating based on that. And this is just kind of a way to kind of hedge against choosing some sort of weird, idiosyncratic subset accidentally just by random. Just to kind of, explain this a little bit more, this threefold cross-validation might be, you split the data into 3 equal parts, A, B, C, fit the model on B and C, test on A. Fit the model on A and C, test on B. Fit the model on A and B, test on C. So basically, eventually, every single data point in your data set has been used in a test set once. Right? So, I just kind of described cross-validation. That's a very popular one that's used a lot. There's a lot of other ways to do this, though. The holdout sample that I was talking about is kind of like a more primitive version. Basically, you just hold out part of your data set. There's also leave one out cross-validation. This is an extreme version of this k-fold cross-validation that I was talking about. Basically, what it boils down to is it's k-fold where k is equal to the number of data points you have. You just leave one out and then train your model on the rest of the data set, predict that one. And then you basically just repeat over and over until every single data point has been used as your one that you left out. There's also random subsampling. So instead of this k-fold cross-validation where you kind of every single data point has been used once in the test set, you instead just kind of randomly pick test sets, and then you just kind of repeatedly take random subsets. And so some data points are going to be used multiple times for the test set. Sometimes some data points might not be used in the test set. But this is just kind of another way of making sure through randomization, making sure that you don't have just any sort of weird results. And then there's also temporal holdouts. This makes the most sense to use when you have kind of data over time. And so what you do is, for example, let's say you have data, multiple years worth of data from 10 years, like let's say 2008 to 2018. What might make sense is to kind of simulate what might happen over time. So let's say at 2010, you think, well, I have data from 2008, 2009, 2010. I want to predict on 2011. So you use 8 to 10 and try to predict on 11. And then you simulate what would happen in 2011. You use data from 2008 to 2011, try to predict on 12, and so on. Basically kind of increasing the amount of data you have over time. And basically, this is just something that kind of makes sense to use when you have that time component in your data. In our case, we really just have one data set of the cars, the horsepower, and the miles per gallon. So we don't really have a time element, so it doesn't really make sense to use that. But yeah, this is just something to consider when you have that temporal element in your data set.